Hello, my name is Connor Boss, and I am a PhD candidate at Michigan State University with the Department of Electrical and Computer Engineering. My advisor is Professor Srivastav, and today I will be detailing our work on cooperative air and ground-based robotic teams for planetary exploration. I will present some of the motivations and challenges to solving this problem. These robotic teams will allow for fast terrain mapping and remote perception, which can aid in longer-range trajectory planning for the ground-based rover. Now we set out to answer the question, what if we could land the UAV on the rover? This would give us several advantages. This could enable rapid recharging of the UAV, could enable sample delivery if the UAV is able to land and collect samples. It would also enable the capability of changing instruments to allow different observations to be made on each flight. Some of the principal challenges of a rendezvous landing, as described here, are that we only have relative positioning information when we fly on other planets. So, for example, there's no GPS. The rover may also be moving when a landing attempt is made. This would require real-time trajectory generation for the UAV to successfully land. We also pose the challenge of making this method resilient to communication dropout. So if the rover can no longer communicate its position to the UAV should still be able to optically pick out the rover and come and land on it. This method also should be robust to modeling errors and external disturbances such as wind gusts. We address these challenges through an extended high-gain observer framework, and pictured on the right here is our experimental setup, where we have a small ground robot to represent the rover, and a hex rotor UAV. I will briefly describe some of the details in our extended high-gain observer framework. This framework can be used to estimate unmeasured states as well as these disturbances. So here we have a plant model for our hex rotor UAV, and we add these disturbance terms which represent any lumped additive disturbance such as wind gusts or modeling error. Now we can use our observer framework to estimate all of the system states as well as these disturbance terms, while only being able to access position measurements from our system. These estimates are then used in our feedback control strategy, so we can cancel out these disturbance terms and very robustly and very accurately track a trajectory with the UAV. Now we further extend this observer framework to estimate the rover's trajectory in real time that will be tracked by the UAV. So if we consider the rover moving as a simple second-order system, we make one small assumption that the control input is a function of the states, which really aids in our analysis later on. We then extend these dynamics to include the third-order derivative of the rover position, because this is required in our feedback control design. We then use our estimator framework to estimate all of the higher-order states while only using a position measurement of the rover. These estimates are then taken as the reference trajectory for the UAV, which will then show that we can successfully land on the rover. Our experimental setup consists of a Q-bot, which is this ground-based robot pictured here. It is manually teleoperated, meaning we have no idea what the trajectory will be prior to starting the landing procedure. So everything will be updated online. The hex rotor that we are using uses a Pixhawk flight management unit, which contains computation and all of the sensing on board. And all computation is in fact done on board this small flight controller. We also use a Vicon motion capture system for localizing both the ground robot and the hex rotor. Here's a video of our experiment where the hex rotor takes off, hovers up to an initial altitude, and then the command is given to track and land on the rover. And the rover is being manually operated, so it's driving around and the hex rotor is autonomously tracking the rover and then successfully lands on it while the rover is still moving. I hope you enjoyed this brief presentation of our work. Thank you.